Hi friends, we are from Group 2 and we are here to discuss on the electronic configurations of elements from the periodic table. Many scientists contributed for the periodic table. People like Berzelius, Cannizzaro grouped the elements by their atomic weights and properties separately. But the great scientist Mendeleev combined these two. His intelligence lies in assuming them like a flash of clouds and grouping them with their properties as well as their atomic weights into a massive slab. He discovered it in 1869. He also predicted few elements with the help of his grouping. For example, check the third column, fifth row in his table. We can find a dash there. The boldness of him is he gave a name for the element as Eka aluminium since it's one step away from aluminium. Based on the location, he said all about its nature like atomic weight that is 68 and properties and so on, which is nothing today's gallium. And his predictions were right. Also scandium, germanium, rhenium and more was predicted by him. But our area of discussion today is not the periodic table but the electronic configurations of the periodic table from the elements 21 to 40 of their atomic number. We will discuss about Bohr atomic model and its acceptations, and we will see an example of the electronic configurations, and we will see how various principles affected the periodic table. Finally, we will have an easy way to remember it. That's it now. We will see it one by one.
Now we are going to see how to write the electronic configuration of elements. Okay. Bohr-Berry rule says that maximum number of atoms that can be accommodated in a particular orbital is given by 2n square. This is an explanation regard to Bohr's atomic model. Consider the orbit number 1. Okay, let this n is equal to 1. So when n is equal to 1, n square is 1, so 2 into 1 is 2. So maximum number of atoms that can be accommodated in first orbital is 2. So in second orbit, 2 square is 4, so 4 2s are 8. So maximum number of atoms that can be accommodated in second orbital is 8. When in third orbital, when n is equal to 3, 3 square is 9 and 9 2s are 18. So maximum number of atoms that can be accommodated in third orbital is 18, and here we have a problem. Here it is said that in third orbit we can accommodate maximum 18 electrons. Then you can have a doubt, that is, for example, consider potassium. Electronic configuration of potassium is 2, 8, 8, 1, but not 2, 8, 9. That is why, you may think, but according to this rule, that is, it can accommodate 18, right? So it must have the electronic configuration 2, 8, 9, right? Then why it is 2, 8, 8, 1? So I'm going to tell you how it is as come. Atomic theory now we are following is Schrödinger rule. So according to modern atomic theory, there is no more orbits. We have suborbits or orbitals. So there are 4 suborbits, that is called S, P, D and F. So S can accommodate 2 electron, P 6 electron, D 10 electron, F 14 electrons. So it will be clear for you that we have 4 suborbits or orbitals. Okay, now let us consider a nucleus and 4 orbits according to Bohr's rule. Okay, so this black color line denotes the orbits and red color line denotes the suborbits. So n is equal to 1 denotes the first orbit, 2 is second orbit, third orbit, 4 and fourth orbit. So in first orbit, we learned that every orbit has suborbits. So first orbit has 1 suborbit, that is orbitals, that is S, and second orbit has 2 subshells or orbitals, that is called S and P, and third orbit has S, P, D subshells, and fourth orbits as S, P, D, F subshells. Like n is equal to 5, n is equal to 6 and all, there is no more 5, 6 suborbitals. There is only 4 orbitals. So for n is equal to 5, 6 for everything, they have 4 suborbits, that is S, P, D, F only. Electrons will get filled in this sequence only. But when we consider energy, that is oneness, you can see here in I have written in this increasing order, right, in brown color. Oneness will have less energy compared to 2s, 2p, 3s, and it will go in this sequence. But there is an exceptional case, that is 3d orbitals will have more energy compared to 4s. So this is experimentally proven it. You can see in this diagram. See, first electron will get filled in 1s, next 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s, and it goes on like this. And this is how we will accommodate electrons in an orbital. Now we will have an idea how to write the electronic configuration of elements. So now let us take the case of potassium. Okay, so now start writing the electronic configuration of potassium in the order I have shown you on image, right? How to write the electronic configuration in order. So refer that and just start to write to the configuration of potassium. So potassium's atomic number is 19. So we'll start to write 1s2, 2s2, 2p6. So 6 plus 2 plus 2, that is 10. Then after 2p you have to get filled in 3s, so 2, so 12 electrons. Then 3p6, how much? 18 electrons. Now after 3p you have to get filled in 4s1, so 18 plus 1, 19. So totally 19 get filled. So now in first orbit, that is there are 2 electrons. In second orbital, 6 plus 2, that is 8 electrons. In third orbit, 6 plus 2, 8 electrons. And fourth orbit, it is 1 electron. And that is why the electronic configuration of potassium is 2, 8, 8, 1. So this will be, I think it's clear for you.
We can't measure the state of the electron more precisely, but using quantum mechanics, one can say where the electron is likely to be and the energy of the electron. For a n electron system with coordinates small r1 to small rn, with m nuclei with coordinates uppercase r1 to uppercase rm, the wave functions psi of small r's and capital R's determines the charge distribution of all charged particles. It satisfies the Schrödinger equation. Arthur Fock found out the way to find the energy of an electron in a specified quantum state. The lower the energy, the higher the binding energy. Using this expression, we can find out the energy of an electron. The electrons in each shell accordingly increase in energy with increasing L. So, the binding energy will decrease with increasing in L. That's the reason why the 4s electron with L is equal to 0 is having more binding energy with comparing to 3d electron with L is equal to 2.
Now let us see the electronic configuration of elements from 21 to 40. 21 is scandium. So its atomic number is 21, right? So we will write 1s2, 2s2, 2p6, that is 6 plus 2 plus 2, 10. Then 3s2, 3p6, that is 6 plus 2, 8. So totally 18 electrons. So remaining 3 more electrons you have to fill. Okay, after 3p, which orbital you have to fill? You have to fill in 4s orbital. That because 4s has less energy compared to 3d. So already it is 18. So 2 electrons will get filled in 4s2. So it is 20. After 4s, electrons will get filled in 3d orbital. So remaining 1. So that's how the electronic configuration of scandium is written. So I think it's understand. Like this we have to write for other elements, but we have an exceptional case in case of chromium and copper.
Because of the symmetry in the charge distribution, the atom is very stable with fully filled orbitals or half-filled orbitals. An atom with only closed shells has no dipole moment. It does not attract other electrons and its electrons can't be easily detached. In this case, the completely filled or half-filled d sublevel is more stable than then a partially filled d sublevel. So an electron from 4s orbital is excited and rises to a 3d orbital.
Now I will tell you an easy way of remembering elements from 21 to 30. So it goes. Sir Titus, very cruel man for class 9 seizing. Hope you all understood this topic very well and our seminar.